One topic tonight from chapter 8. It's going to be a little bit of a shorter class tonight. I'm just going to gently introduce us to chapter 8. So not that long. I'm going to give you the whole concept and then do 3 or 4 examples and send you on your way for a weekend. So at some point, probably sometime tomorrow or late tomorrow, I'm going to send out a solution sheet to the test questions. I just got to make sure. So all 5 of my classes this week had tests. So the last couple of days, I know I probably got like 200 unread emails. I haven't even looked at my email today, I'm afraid. So it's going to take me quite a while to get the tests all graded, but I will be sending out solutions so that you'll at least have an idea. Now, some of these problems, there were sort of slightly different ways you could do it. So if your method isn't the same as the one you see on the solution sheet, doesn't mean you're wrong, just means you did it a slightly different way from me. I will tell you that one of those questions on the test was an extra credit question, but I just didn't tell you because I wanted everybody to give it a try. So there's one extra credit question on there. If you got it wrong, doesn't matter. And if you think back at some of those questions, you can probably guess which one it was. Okay, so let's see. Questions about anything before we get started? Anybody got any questions about anything? Well, all right. So we're done spinning things around. No more rectangles, no more shell, no more blue man, no more red man. Nothing going round and round anymore. So chapter 8, when you got to the end of Calc 2, you learned some basic integral techniques. The power rule, trig rule, the sines and cosines, e to the x, you could probably do, and you learned maybe some basic u substitution techniques. So that's where you got to the end. In chapter 7, the integrals we did weren't really a big deal. Most of those were just plain old polynomials. You probably got to the point where you're just doing them in your head. So chapter 7 wasn't about the integrals, it was about using them. So chapter 8, we're going to have, I think, 1, 2, 3, 4, I think it's 5 techniques to do integration that you didn't know how to do. So tonight we're going to do something called by parts. And it's the first technique we learn, and I'm going to explain a little bit about what it all means. So first, a little trip down memory lane. Way back to the whole thing. So when we do derivatives and integrals, differentiation and integration are things called linear operators. A derivative and an integral operate on a function and turn it into something else. So it operates, does something to it. And linear, I'll get to that in just a minute. So in Calc 1, whoops. 2/3 of Calc 1 was about derivatives and then using them for things like optimization, related rates, that kind of thing. And Calc 1, you learned maybe 17 derivative rules. So the power rule, the quotient rule, the product rule, the chain rule, trigonometric rules. The derivative of ln is 1 over x, derivative of EX, and then you just use them for a little bit. Once you do a derivative, you get down here. So you take a function and do a derivative, you get f prime, which is just another way of saying derivative. Then you did integration. Even though we don't always think of it this way, you can think when you do an integration, you can think of that function as the derivative of something, and the integral tells you what the original function is. That's one way to think of it. But when we do an integral, we don't quite get all the way back. We never get all the way back. Why not? Why can't we get? Wait, I couldn't hear you.
The constant?
Yep, that's right. So, Mikhail, you lose a constant. If you have y is equal to x squared, that derivative is 2x. The integral of 2x is x squared, derivative of x squared, 2x. But if you have y equals x squared minus 3, that derivative is still just 2x. That 3 gets lost forever. And that's why we always put the plus c on the end of it. That's called an indefinite integral because we're definitely not sure what that constant might have been on there. So the other thing about derivatives and integrals is they are inverse operations of each other. They undo each other. Like if you square a square root, it goes away. If you do the square root of something squared, it goes away and you just get the function. So these things undo each other. Although, a little history trivia here. So calculus started back in the 1700s. Most famous name of that is Isaac Newton. There's a whole bunch of other people. And he developed the techniques of doing derivatives because he needed to find out the slope of a tangent line because he knew that meant the instantaneous rate at which something is changing. So when he was doing gravity and all that kind of stuff. And so he came up with the idea of doing derivatives. Well, found him. He also knew that the area under a curve had physical meaning as far as energy and physics, so he developed the way to do integration. Strangely enough, it wasn't until about 150 years later, or 100 years later, that anybody knew the connection between integrals and derivatives. They didn't have this nice notation that we use on here. Okay, so that's the relationship. So in chapter 8, we got to keep both of these in mind. Yeah. You remember the chain rule from Calculus 1? Remember hearing the chain rule? That ring a bell? It's been a while. Probably since you had Calc 1, everything went into lockdown after that, so our memories are maybe a little bit fuzzy. So the chain rule is like this. If you have a if you have a composite function is a function with another function inside it. And to do this derivative, anybody remember what the derivative, how the chain rule derivative works? Rattling around in your brain somewhere. So the chain rule works like this. You do the derivative of the outside function, but you don't do anything to the inside function. You don't touch it. And then you multiply by the derivative of the inside function. Mariana, exactly. Yep. Even use the fancy symbols. Very good. So if you look in the chat, I was going to say comments. So Mariana has written it more officially. Instead of f of x, I just wrote f. And instead of g of x, I just wrote g. I was being lazy here. So she actually wrote it the correct way. Okay. Now, so this way is the derivative. But suppose we go the other way. In the other direction, we would get what? We would get the integral. Now, you already know how to do an integral of this. You already know it, but you've never thought about it like this. It's a little technique you learned in Calc 1. When we did the arc length and the surface area problems, it's an integral technique that came up quite a bit in those problems. When you're doing arc length and surface area and all that, chapter 7, what kind of integral did we often end up with that we had to do how?
U substitution.
Yeah. That was good. That was you, Brandon?
Yeah.
Yeah, so the technique of U substitution undoes the chain rule. So the chain rule derivative sends you this way To do U substitution takes you back that way. So they are inverses of each other. So think of it like this. The chain rule kind of unpacks things. The U substitution packs it all up again. So think about this. You're going to go on vacation to a hotel, back in the ancient days when we could do that kind of stuff. So you go to the hotel, you put everything in your suitcase. When you get to the hotel, you unpack your suitcase. It's in the room. When it's time to go home, you pack your suitcase up and you go back. That's essentially what a U substitution does. So if the thing you're integrating came from the chain rule, you integrate by U sub to put it back. And that's one of the things we're going to do here tonight with this. We're going to learn how to go backwards from the product rule. All right. Remember what the product rule was? Well, the word product means to do what? It's the word product means. It's the real word for
multiply.
Yep. So if you have two functions multiplied together, f times g, if you want to do that derivative, how does the product rule work? Remember?
Derivative of the first times the second plus derivative of the second times the first.
Perfect. It's f prime times g plus f times g prime. Each one takes its turn. If you had 5 functions, it still works. Now, a lot of textbooks write this the other way. I always write it this way, and it doesn't matter because the plus sign addition is commutative. I do the first one first, don't touch the second, leave the first one, and then do the second, all right? Equal signs go both ways. So in this direction, this is the derivative. But if our integral has this in it, then we have to go backwards. And that's called, that method is called by parts. And that's what we're going to do tonight. I'm just going to do a few examples. So we're in chapter 8, we're in section 8.2, not 8.1, leaving that alone. But I'll be taking pictures of the textbook and sending all that. So that's what we got to do. So there's a simple little formula that we use. I'm just going to show you quickly where that comes from because it's nice to know that formulas come from somewhere. Questions about anything so far? I haven't really said much yet. Questions? Okay. So, I'm going to do this. Now, for reasons I've never been quite sure of, every calculus textbook ever, and every college over the whole world, when they do the by parts formula, they don't use F and G, they use the letters U and V. It's just letters, it doesn't matter. I'm not sure why they do, but they do. So we're going to do it like this. We're going to let the letter U is just going to be what f of x is, and the letter v is just going to be what g of x is. So if we do the derivative with respect to x of u times v, it turns into this. The derivative of u is du, and then we have v plus u times the derivative of v, which is dv. This is nothing different from what I just wrote. This is f, this is g, this is f prime, this is g, this is f, this is g prime. It's just notation change. All right. 2 steps. Here comes the formula. Now, I use the term linear operator. So what I'm going to do is integrate all of this. We're going to integrate this whole thing. Now that might look a little strange to you. We're integrating an equation, but we can do that, right? Essentially, in algebra, when you do something to one side of the equation, you have to do it equally to the other side of the equation, which is really what algebra is all about. So I used the term a little bit ago called linear operator. So don't write this down. I just want to give you an example. A derivative and the integral are linear operators. Don't write this down. I'm just going to give you an example. If we integrate 2x plus cosine x dx, all right, we're just going to do this integral. You probably do this in your head. So what's the integral of 2x plus cosine x? What is that integral?
X squared minus sine of x.
Oh yeah, you're good. You got the negative sign right. How confident were you about that?
Pretty confident.
Good. And one other thing. Forgot something. The classic. You forgot the classic.
Plus
Man.
C.
Let's see. Yeah. Remember?
Okay.
We didn't see those in chapter 7. We didn't see the plus C's in chapter 7 because when there's no limits here, no numbers, this is called an indefinite integral. And so you have the plus C on it. Chapter 7, we had limits, numbers here. So our answer wasn't another function. Our answer was just a number. So you forgot all about those plus C's, right? Now, here's how you did that. So when Brandon did that, he looked at this and he did this integral. And then he looked at that and he did this integral. We're integrating the whole thing, but because this is a linear operator, you can do each one separately. Essentially, that's what it means to be a linear operator. So we can, because this is a linear operator, I can integrate everything up here separately. So we can do the integral of this, we can do the integral of this, and we can do the integral of that. This is not so this is incorrectly written. To do this integral, I have to put the v inside there, so I have to rewrite this. Okay, those three integrals. Oh, wait a minute. Oh, no, wait, sorry. This just works like this. Oh, there we go. Those are the integrals. All right. So I just changed colors. But what happens on the left-hand side here? What does all of this turn out to be? This is a derivative. I'm doing the integral of a derivative. What happens when you do the integral of a derivative or the derivative of an integral?
They cancel each other out.
Exactly, like matter and antimatter, they disappear. So what happens over here is you just get UV, right? Okay, here comes the formula. We're all ready now. I'm just going to rearrange all of this. This is completely correct. Everything here is working, but that's not the way the textbooks write it. That's the by parts formula right there. That's it. So notice, when you do an integral by parts, you end up with another integral that you have to do. So we're going to do some examples here. Sorry, still Still losing my voice here. All right. Yeah. What's the integral of just plain old e to the x?
E to the x.
Yep, just e to the x plus c. But if we do the integral of x times e to the x dx, now we need to do by parts. There's no basic formula to this. So this is this part right here. So we have to do this integral. All right. So first, some just verbal information. When you did derivatives in Calc 1, you learned, like I said, about 17 rules or something. And then you go home and do some homework and you look at the function and you think, oh, I use this rule to do that. Here's another derivative to do. I use this rule. Doing derivatives is pretty straightforward. Integration is none of that. There are more than 100,000 formulas for integrals, and none of them are going to work most of the time. So you have to finagle stuff, you have to fuss around with it. So one of the frustrating parts about chapter 8 is going to be, it's not always obvious what method to use. So one of the techniques in chapter 8 is, when you have an integral in front, is just to stare at it for a while and think about all the different methods once we learn them. And then you try one, maybe it doesn't work. Try another one, maybe it doesn't work. You manipulate the function inside so it looks different. Now maybe something will work. When we're doing integration, there aren't any rules where I can tell you, always do this. It just doesn't work that way. The best I'm going to be able to help you with is, when you see a function that looks like this, try this method first. If it doesn't work, then try this one. That's about as good as it's going to get here. So what we have to do is come up with the parts. The integral has a u and the integral has a dv. We have to find those. We need to know what u is because we need to find du. We need to know what dv is because we have to create the v. So to do by parts, we have u and we have dv. And with the dv, always goes the dx, always. So here's how this works. In this case, our x is going to be the u, and the ex dx is going to be the whole dv thing here. So here's our parts. We got this part, and we got that part. That comes out of the problem. It's not always going to be obvious which one goes where. Sometimes you're going to try one and it's going to lead you down a dead end and you're going to whack into a brick wall. So you have to go back and try different ways here. So you have to practice a lot in chapter 8. All right. We need to have a du. Well, we get that by doing this derivative. The derivative of u is the derivative of u. If I do the derivative of that side, I have to do the derivative of this side, and the derivative of x is dx. We need to have a v for the by parts formula. Well, how am I going to get a v from this dv? What am I going to do to dv in order to get a v? How do I turn that into a v?
Integrated?
Integrate it, yep. I'm going to integrate this. But if I integrate this side, I have to integrate this side. That's why we need the dx. Now, this is the last time for the whole thing with by parts. I'm not going to write the integral signs anymore. I'm just going to sort of do it. The integral of 1 dv is just v. And the integral of e to the x dx is e to the x. Now, we need a plus c. I'm not ignoring it. I'm not forgetting it. We need a plus c, but we aren't going to do that until the until the end of the problem, we're going to put it on. Oh, Kayla, I have a file on my calendar. Oh, Kayla just sent you a yeah. Is that something I wrote, Kayla?
No, I typed that up last year.
Oh, okay. Because at some point I wrote one of those too. But did you like get it from the book kind of thing?
Just book experience. I think you looked over it.
I do remember that. That's nice. Yeah. So the lovely Kayla has a guide sheet for chapter 8 about if your function looks like this, try this. And it's not always going to work, but it's a really good, it's a really good, oh man, it's a really good, helpful thing. Thank you, Kayla. Okay. So we've defined our parts. Now we use the formula. Everything goes in place now. U times V is U times V. This gives us X e to the X. So that's U and that's V. Then comes a minus sign. And sometimes that might turn into a plus sign, but depending on what's happening here, minus, and then we do the integral of V du. So there's where all the parts go. I'm going to pause there for just a second, partly to see if I can get my voice working. So this is all going to seem a little mysterious for a while. We're not going to do very much tonight. I'm just going to like practice some of these for a little bit. After you do 2 or 3 of them, you'll begin to get the hang of it. Okay. Now, once you've done this, you never touch it again. But we do have to do this integral. What's the integral of negative e to the x? What's that integral? The integral of negative e to the x.
Negative e to the x
Yep. Negative e to the x, and then we need a,
plus c.
there's where we put the plus c. So that's the answer. Now, normally on a homework problem, I often use the even numbered problems for the classroom examples. You get the odd numbers. You go to the back of the book and you're going to see that and you go, okay, yep, I did it right. You move on to the next problem. Here's a big piece of advice I can give you in chapter 8. One of the very best things you can do to enhance your talent at this is to do the derivative of your answer and make sure you get back to where you started from. So that's just doing the derivative of your answer, checking your own answers will really help you learn the connection between derivatives and integrals and all that. So we're going to check this solution. We're going to do, yikes. My laptop is now a floor top. We're going to do the derivative of the solution. X e to the x minus e to the x plus c. All right, we're going to do that derivative. What's the derivative of the constant?
0.
0. Not even going to write it. What's the derivative of negative e to the x?
Negative e to the x.
Yeah. So a lot of people don't like e's. They see e's and they're like, oh my God, e's. But it's just, they're easy. The integral of e to the x, derivative of e to the x is e to the x. I always tell people that the e stands for easy. It's not really true. Anybody happen to know what this e actually stands for? So e is a number, right? 2.718, blah, 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 blah. It's an irrational number like pi. So this number, just like pi, is given a letter. Anybody know what that letter actually stands for?
Is it exponential?
Good guess. Good guess. Excellent guess. It's not right, but it's an excellent guess. Yeah, Kyle has it down here. It stands for a guy's name. His name, which is pronounced Euler, not Euler, it's pronounced Euler. He was a huge mathematician in the 1700s. He discovered so much math that even in the 1700s, his math is used in computer science. It's used in biological and medical procedures to find the best way to do something. So it turns out that this number that he ended up calculate by looking at nature. Oh, and what goes with an e to the x? So e to the x and ln x are related, right? They're inverses of each other. So it turns out, so what does the n stand for in ln? What's the n stand for?
Natural?
Yep, this is the natural log. It's actually Latin, logus naturalis, but it stands for the word natural because e to the x and ln to the x show up everywhere in nature. They determine to a certain extent the shape of a spinning galaxy. They determine a lot about how DNA works, how plants bloom and blossom, how the seeds of a sunflower arrange. So he found this everywhere in nature and came up with that number. So this is named in honor of him. So there's your trivial information for tonight. Okay, that derivative is 0. This derivative is negative e to the x. Now we have to do this derivative. How do we do the derivative of this?
It'd be the chain rule.
No.
Oh, the product rule.
Yeah, this is the product rule. And so you see, when we integrate by parts, a product rule comes out, which means when we do the derivative, the product rule is there and gives it the integral. So that's why the connection between product rule and by parts. So the product rule, the derivative of x is 1 times e to the x plus x times the derivative of e to the x, which is e to the x. And what does all of that equal?
X e to the x.
Oh, x e to the x, plus c. And this was the thing we integrated. We got right back to the integral. So doing the derivative of your answers is a very, very healthy thing to do. And by doing that, a lot of times what happens when you do integrals, the biggest sort of little mistakes I always see is like messing up on the constants. Like if we had a 3 in front of this or something, it's easy to, that will catch the constants on that one. Now, it won't be always true. When we get to the section in chapter 8 called trigonometric substitution, we turn things into sines and cosines of thetas. Doing the derivative of your answer, you might not get what looks like the function you started with, even though it is. All right, so that's our first example tonight. Any questions yet? Just going to do 2 more. That's all I'm doing tonight. All right, on to the next one. All right. The integral of sine is negative cosine, but we have x times the sine, so we need to do by parts. We need a u, and we need a dv, and always with the dv goes the dx. So now we have a choice. We can let the x be u, or we can let the x be dv. We can let sine of x be u and sine of x be dv. How do you know which one to pick? And here's the answer you might not like. You know, if you practice enough, you'll build up an intuition for which one to try first. There are no rules that say always do this. Kayla's little sheet that she has for you over in the comment section down there will give you some guidelines. So I'm going to pick the wrong ones right now to show you what can happen. Don't write down what I'm going to do. It's going to be wrong. It won't work. I'm going to put sine of x over here. I'm going to put the x over here. This isn't going to work. Now, what's the derivative of sine of x?
Be just cosine.
Just cosine. And don't forget, you need to do the dx when you do the derivative. What's the integral of what's the integral of x dx? Just the integral of x dx. It's just 1/2 x squared. Okay. Now, the derivative of sine is cosine. The derivative of cosine is essentially sine. Putting the sine here, I didn't get anything more complicated here. I got something basically the same. I got a basic trig function. Over here, when I did the integral of x, I created something more complicated than I started with. This integral just has x to the first in it. Now I have to deal with an x squared. I made the problem more complicated. I don't want to do that. So when we go in to put this into the formula, oops. When we put this into the formula, now I have to deal with the integral of an x squared times a cosine. I just made this problem worse. So that's a hint that that was not the right thing to do. It's not a rule, but it's a guideline. When you pick what you're going to choose for u and dv, pick a u that when you do the derivative, you get something not more complicated, and pick a dv so that the integral is here. So generally speaking, at least in this course, in this textbook, if your function you're integrating has a sine or a cosine or an e to the x, let that be the dv because they're easy to integrate. If you integrate sine, if you do integral of sine 35 times in a row, all you're going to keep getting is sine, cosine, sine, cosine, sine, cosine, time, cosine, right? Nothing gets more difficult, ignoring the negative signs here. So the correct choice for this problem is this will be the x and this will be the sine of x. Derivative of both sides, du, derivative of this side, dx. Integral of dv is v, and the integral of sine is, it's a cosine, but which one? Integral of positive sine gives me,
Negative?
yep, negative sine of x, and the plus c comes out later. All right, so I'm just going to pause there for a second. Anybody got a question about anything yet?
So you're doing the integral of dv, right?
Yeah, you integrate dv to get v. I'm just not drawing the integral signs anymore. That's why you have to have the dx over here. If you're going to integrate, you need, this is called a differential. When you integrate, you have to have a differential here. That's why the dx goes there.
So is v just negative cosine? I'm just confused.
Oh, I wrote sine. I'm sorry. I think I said negative. Yeah, sorry about that. Thank you. Did I mess that up, or was I just seeing if you were paying attention? You'll never know, will you? Okay. Now we put all of the parts up here. So we have u times v. So u times v is negative x cosine x, u times v. And then we never have to do anything with that again. Now, The formula has a negative sign here. I showed you where that came from, but there's a negative sign down here, so that's going to make that positive. And then we have the integral of v times du, and we get cosine x dx. Okay. Are you starting to miss spinning rectangles around yet? Probably not. That was pretty dreary after a while, wasn't it? It is pretty dreary, but it's part of the course. I got to do it. I get to pick how to do it, but I don't get to pick what to do. All right, so here we go. So this integral now is equal to negative x cosine x. And what's the integral of positive cosine? Integral of positive cosine.
Sine.
Positive sine. And then we put the plus c on. Instead of plus c, I'm going to use plus k because I already got a letter c here. So k also stands for constant. It's just in German instead of English. All right. Oh, in general in math, not always a true. Why is it positive cosine in the integral? Oh, so Hannah, the formula has a negative sign in it. That's part of the formula. In this particular problem, our v came out to be negative. So we had dv was sine of x dx, right? That was our dv. And then we integrate it. So we get v. And when we integrate sine, we get negative cosine. So this negative sign turned that negative sign into a positive. We had negative, negative. Yep, you got it. Negative signs have been troubling ever since you first learned them, everybody, right? Like mosquitoes that buzz around, you drop one, you do a problem in physics or something, it's 3 pages long, got the wrong answer, and realize you missed a negative sign like 20 minutes ago. Yeah, they're pretty awful. All right, so there's our solution. How do we know that's right? Well, let's do the derivative. So we're going to do the derivative of all of this. All right. Derivative of a constant, 0. The derivative of positive sine is?
Cosine?
Positive cosine. And now to do this derivative, we need the product rule because it's this times that. Product means multiply. So the derivative of x is 1. That leaves me with negative cosine x. And then we get negative x times the derivative of cosine. And the derivative of cosine is?
Negative sine.
Which makes this positive. These two cancel out, and we're left with x sine of x, which is the thing we integrated. So it worked. So lots to pay attention to here. Not so much got to watch out for negative signs, got to often when we begin chapter 8, it's very easy to get a derivative and an integral mixed up because you're just not used to it. So I'll often hear, you know, what's the integral of x squared? Somebody will tell me 2x because in their mind they're thinking derivative. Those aren't issues of intelligence or understanding. Those are just issues of just, you know, not paying attention. So watch out for the details. All right, one more example. And then just a couple of comments. So first of all, what's the integral of 1 over x? The integral of 1 over x.
Ln x.
Ln x plus c. And the method for that is just to know it, right? There's no calculation going, well, there are, but they're complicated. The 1 over x integral is just something you just realize. So the integral of 1 over x is the ln of x. That means the derivative of ln of x is 1 over x. That's how they work, okay? All right, good. What's the integral of ln of x? We have to do this by parts. Now, in this problem, there's no question. The dx has to go with the dv. That means the ln of x is the u. There's no choice here. Okay. The derivative of u is the derivative of u. The derivative of ln of x is 1 over x, and don't forget the dx. The integral of dv is v, and the integral of dx is x, plus c, but that goes on later. Okay, and then we put these into the formula. uv minus the integral of v du. uv minus the integral of dvu. Something I've noticed from students that I've had from 15 years ago and 20 years ago, you know, engineers are out there being professional. One of my students currently, she's 28 years old. She is now a trauma surgeon, an emergency room surgeon up in Queens. I have students do all kinds of things. 20 years later, they can still recite uv minus the integral of v du. They might forget how to do them, but they still remember that. All right. U times v is x times the ln of x. Well, that's actually v times u, but it doesn't matter because multiplication is commutative. So you usually put the ln x at the bottom, minus the integral of v times du. I ran out of room there, sorry. Everybody good? Any questions? So always with by parts, you end up with another integral that has to be done. Oh, and sometimes you end up with more than one integral to be done. I'll explain that in a minute. Well, x times 1 over x is what? Do that multiplying, what do we get?
1.
Yeah, 1. So this just turns into negative the integral of dx, which is just minus x plus c. That's the integral of the natural log. And now I'm going to do the derivative and check it. All right, derivative of constant is 0. What's the derivative of negative x? Derivative negative x.
Negative 1.
Yeah, see, it's taking a little while to think about that, isn't it? Because you haven't done derivatives in so long. So this gives us negative 1. And this derivative is product rule. The derivative of x is 1 times the ln of x, whoops, plus x times the derivative of ln of x, which is 1 over x. So this becomes ln of x plus 1 minus 1, which is ln of x, which is what we integrated. So we got right back where we started from. So again, do the derivative of your answers. Good for you. All right, any questions? Okay, couple things before we take off. One thing is, first of all, about the textbook. There's things I like about this textbook. There's things I don't like about this textbook, which is true of any textbook, by the way. One of the things I like that this guy did, so we're in section 8.2, which is entitled by parts. So I'm going to send you out some homework tonight. Not a lot, just a little bit to get started. So you'd think, oh, this is by parts homework, so all of these are done by parts. And you would be wrong. I like that this guy does occasionally puts some homework problems that can't be done by the method in that chapter. So for example, in the textbook, number 14 is this. Number 14 is the integral of e to the 1 over t, all of that over t squared dt. That can't be done by parts, but he doesn't tell you that. And that's going to happen all through chapter 8. Almost all of the problems you get will be done by the method of that section, but every now and then he slips one in. So you have to make sure it's not being tricky. It's being realistic, because life doesn't always tell you, okay, this is going to happen tomorrow, and it happens exactly like that. I mean, life just doesn't work that way, right? How would you do that integral? Oh, and if you don't like t's, you can change everything to x's, but that's all right. How would you do that integral? You do know how, even if you don't know that you know how. Anybody want to venture a guess?
Is it the quotient rule?
Quotient rule applies to derivatives, not integrals. But I'm glad you said that. See how easy it is to get differentials and integrals mixed up? You haven't done derivatives really since Calc 1, and I don't know, that's Calc 1 is at least a bunch of months ago. For some of you, it might be more than a year ago. So quotient rule is a method for doing a derivative. But there is an integration technique that you know how to do.
I think I would try and bring the t squared to the numerator and then make it negative and then just integrate each part.
Oh, but you can't do that. If you have the integral of f times g, you can't just do the integral of f times the integral of g. Doesn't work like that. That's a by parts problem. Yes, if you look over in the comments section, John P is right. This is a u substitution problem. I'll show you how to do it. Very nice, John. You let u equal 1 over t. The derivative, now 1 over t, you can rewrite, as Brandon said, t to the minus 1. The derivative of this is negative 1 over t squared dt. Well, we have a t squared on the bottom and we have a dt. So this problem turns into negative the integral of e to the u du. That's an e to the u problem in hiding. And the integral of negative e to the u is negative e to the u. And that would give me negative e to the 1 over t plus c. That's the answer to that integral. It's not by parts, it's u substitution. So it's not a lot of these. There's maybe, this might be the only one in the section of the homework I'm giving you now. I'm just giving you a heads up. All right, something else that can happen, and we're going to do more of this on Tuesday. This is just like a gentle introduction. Or would you rather go back to swinging rectangles around? Probably not. All right. So we know from before that the integral of x e to the x dx is equal to, you have it in front of you, it's x e to the x, and what came next? Minus e to the x plus c, is that correct?
Yes.
It was the very first example I did.
Yeah, that's right.
Okay, now, suppose we had x cubed e to the x dx. This problem is still by parts, but you're not going to do by parts once. Guess how many times you have to do by parts? You have to keep doing so you do the first time you do by parts, the x cubed is going to end up in the integral, you're going to get x squared e to the x. You have to do that by parts, and that's going to give you an integral of just x e to the x, and you have to do by parts again. So sometimes a by parts problem involves having to keep on doing by parts in there. We're not going to get crazy with this. I think there's 1 or 2 times in this section where we'll have a problem where we have to do by parts twice, and that's all. So that's something else to watch out for. There's one problem in the homework that I'm sending you. I forget what it is. It's not x cubed e to the x, it's x squared e to the x. So you're going to end up doing by parts. So you do by parts the first time, and the integral that comes out of the formula will require you to do by parts again. So you got to practice a lot in chapter 8. I would recommend not trying to sit down and do a whole bunch of problems at once. Just do one problem and go out and do something else for a while. Come back in a couple hours, maybe do one more problem. Just try and spread it out a little bit. You'll learn better that way. All right, questions about any of this? So sometime tomorrow, don't know when, I'll send out a solution sheet to the test questions. It's going to be a while till I get the grades back and everything, so just be patient. But and never throw your test papers away. Keep them all the semester, by the way. But at least you'll have the answer sheet, and you'll have an idea of, oh, okay, did pretty good on here. At least you'll have an idea. All right. So if anybody's got anything else, I'm assuming nobody's objecting to getting done early tonight. Well, all right, folks. I won't see you again until Tuesday, so have a really good weekend.
Take care.
And if you email me, by the way, like I said, all 5 of my classes were hitting me up with tests today. I know I have at least 200 unread emails waiting there, and I'm terrified to open and look at everything. It's going to be overwhelming. If you email me in the next 2 days, you might not hear back from me a while. You might just, email is in the crowd there somewhere, okay? All right, folks, good night. Enjoy yourselves. Drive home safely. Bye.
Thank you.